Great. Well, welcome everybody. I'm going to do an overview of the kernel client, uh, uh, the kernel CephFS client anyway. And so first thing, I also got I kind of have like a syllabus here for our, well, I'm going to try to share the link to this, but I can't figure out how to get it to make a public link for everyone. So if anybody's outside Red Hat, they may not be able to see this. I'll paste it in here anyway. So you should be able to, and it's basically just kind of what I'm going to cover in this talk here. So it doesn't look like a lot, but that last little bit of walking through opening and reading and closing a file will probably take most of the hour. So in any case, first thing that we should realize is that there are lots of the CephFS driver is a VFS driver first and foremost, right? It is basically it implements a file system, which is the magic of Linux really is the fact that it has a unified VFS. You can access a file and generally in the same way, regardless of what sort of file system, what sort of backing it has. That is a marked contrast to most older operating systems like DOS or even Windows, which often needed really specialized libraries and things to access files that were maybe exist on a different sort of back-end environment. So the other thing that you should realize too is that the VFS itself is object-oriented. Maybe a bit of a surprise for people coming from C++, but we do implement object-oriented stuff in C, and the way we do it, it's a little clunkier than it is in C++, but it does work for us. That's the way we operate. So we are doing our own memory allocations, frees, and stuff like that. We have function pointers instead of actual methods, that sort of thing. But overall, it is an object-oriented system. So first of all, if you look at if we look at how how it is laid out, what you find is that we have this sort of network of structs, right? And the structs have things have operations structs in them. So, for instance, if we look at sort of the first stop we can look at here is the superblock struct, and the superblock is sort of describes a mounted file system. Oops, let me do it. This is that. So, in any case, here's the superblock struct that if you look here to the file include Linux fs.h is where most of the file system definitions are. But if you look here, you can look through here and see there's a whole bunch of fields and stuff. But the one that we are primarily interested in is I gotta find it. Super operations. See here, superblock in particular has a bunch of different operations. It's got ones for quotas and exports if you want to export via NFS, and you're doing FS encryption, that sort of thing too. There's separate operations for those as well. But if we look at the super operations struct, you see here we've got a whole bunch of function pointers, and those do effectively allow us to look at or to do different operations. Like if we want to allocate an inode, right? We have to do that. We have to call in this alloc inode, or the VFS will call in this alloc inode struct for a new inode for a file system. Same with destroying and destroy inode, free inode. And a lot of these things are not named very well, and some of them have morphed over time, right? Some of them had different functions at one point in the calling conventions. other things have changed. That's the other thing you should realize about Linux is that the internals are very fluid, and so things change all the time. Okay, but in any case, we can look here at the superblock, and the superblock really represents a mounted file system. So whenever we mount a CephFS file system, we get this, it will allocate a superblock structure and do a bunch of work to fill this out. I'm not going to go into the mounting process here. Complex. But basically what will happen is we'll get this, and then we will also allocate a CephFS a CephFS client struct, and then that will, a pointer to that will end up in this CephFS info. So if we look here, CephFS client, whenever we go to create a new file system or to mount up a new file system, we'll it'll allocate a superblock struct, and then we'll allocate one of these guys. And so it has a pointer back into the superblock struct, but it has a bunch of other fields as well. Here's one for just the Boolean for being block listed, for instance. There's a Boolean for have copy from to, which is a particular operation that the OSDs can do, and so on and so forth. Right? We've got a bunch of others, a bunch of stuff for debugFS entries as well. Work queue structs in here. We have inode and cap work queues. I'll talk about work queues a little later. But in any case, we've got a bunch of these. Got one of these objects per mounted file system. Beyond that, we end up to there's a struct inode, right? A bunch of these here. So here's the struct inode structure, right? So this, a struct inode, most of you guys know, is represents a file on disk, basically, or file or directory on disk. It also does things. There are also other things are backed by those as well. Symlinks, name pipes, all these sort of exotic inode types are also have an inode structure as well. And so anyway, we've got a bunch of these. A running kernel will have tons of these at any given time, right? And so we have to, they're cached and whatnot. But in any case, the struct inode also has an associated Ceph struct to it. If we find the Ceph inode info here, so this is actually what a real Ceph inode looks like, and you'll notice that it has this object, has a DFS inode embedded inside it. So in some cases, some of these structures in the kernel will allocate an auxiliary structure and just keep a pointer to it. Other times we do things that like embed the thing inside it. So in this case, the VFS inode is embedded inside. We also have this thing here, this Netfest Context. This is fairly new. But the Netfest layer that we're starting to use in Ceph has an associated struct per inode where it tracks it as well. And so we embed one of these inside there as well. And so they have to be, and the way we lay these out in a particular way, because when occasionally we have to go back and forth between the Ceph inode info and the VFS inode or the Netfest context. So these have to be in predictable locations inside the struct. We can't randomize those or anything. Beyond that, we've got a bunch of other fields. Here's the vIno, which is tracks both the snap ID and the inode number. There's the iCeph lock, which is a special spin lock that we use to protect most of the Ceph specific stuff. So on and so forth, right? We've got a bunch of other fields in here too. I won't go into them in too much detail. Now, after the inodes, so an inode represents a file on disk or a directory on disk, right? But the path name to that file is stored differently. So kernel, we store that in an object called a Denture. And so the struct Denture is this, and the Denture is what represents a path name component in the kernel. So what we will do is, when you go to do a lookup or something like that, or we pass in path names all the time, and this is one of those things in the kernel that is hugely performance critical, right? We deal with we have to deal with path name walking all the time. Most system calls that we do take many of them take a path name, and so we have to be able to walk that path and do that efficiently. And so the Denture is what is really Linux has the most advanced method on the planet for doing all this stuff, much better than any other commercial operating systems. So we have we track each path name component as an individual object called a Denture, and then there are it keeps track of like where the parent is, who the parent of this Denture is, and then there's every Denture has an inode associated with it or not, in some cases. So and so then it has like here's where the name is stored if it's small enough, so on and so forth. We have this thing called a lock ref, which is sort of with a reference counter and a spin lock embedded together. And so this, so in any case, the Denture cache in particular is highly tuned. And so, and there's a great document in the kernel sources on path lookup and how that all works. Quite complex. So, but in any case, a Denture object is what we're is the interesting bit. So you can see the operation struct here, the Denture operations, right? Oops, sorry. Denture operations. Okay, so here's the Denture operation struct. We have, there's a bunch of different ones depending on, on how they get hashed and revalidated and so on and so forth. And then we also have this field called DFS data. And so we'll have a Denture info, what it's called. Yep. And so every time we create a Denture, a Ceph Denture, we allocate one of these structures and set the pointer to it. And it also has a back pointer into the Denture as well. And so here there's things like whether we have a lease for it and how what sort of generation it has. There's a flags field, so on and so forth. Right. All right, and beyond that, we have this thing called file. And then finally, the last object I'll cover is struct file, which represents an open file description, right? So if you go to open a file, we have a record of that open file, all sorts of info we have to track, like where the current pointer to the inside the file is, where the current position of the file is, there's how the file was opened, whether it was read only, read write, that sort of thing. All that stuff is tracked here inside this thing we call struct file, which is technically we call a file description. Most of us are familiar with file descriptors. The file descriptor is just a number, but it is a number that is indexed to a particular structure in the kernel, and that kernel is the struct file. And we also have the, of course, it's got its own operation struct too. And so we have this, there's a whole bunch of file operations here, right? And once you've opened the file, you can read from it, you can write from it. We also have readitor, writeitor, which are, were added later. And this is another thing you'll notice in the kernel. Sometimes, because we have so many file systems, it's really hard to change, these operations all at once, right? So what we find a lot of times is that people will add new ones and patch some of the file systems to them, and then leave the rest as rest to be done later. We have that here in this case, right? There are some file systems that were never converted to use readitor, writeitor, and so they use this old style read write struct. And we have handling for old style read write operations, and so we have handling for both in the kernel and in some places. Well, we'll see that point later. And then we have this like iterate, shared here. A lot of these names are not very descriptive, unfortunately. Iterate, shared is all about reader. That's done. And here's fsync, right? So anyway, we got a bunch of these. So now I was going to go through and does anybody have any questions so far? If you have any, go ahead and speak up and I'll answer them. But if not, I'll just keep going. All right, I'll take that as a no. Now what I'm going to do is cover like what happened. We're going to cover a real simple thing, right? Which is, let's suppose we want to open a file on a Ceph file system, right? Just open it read only. We're going to read that file in the first 4K or whatever, the first page, and then we're going to close that file. Right? Well, let's walk through how that actually works. So the first thing we do is whenever you call into the kernel or whenever you call a system call, right? What we usually call it through libc. So libc will then go and stuff the right arguments into all the registers or onto the stack, dispatch into the kernel, depending on your architecture, and it does it a different way. But anyway, it will do that. And so the first thing we're going to do is 4. Yeah. So when we go to, in this case, we're going to do an open, right? And basically all open does is it has this syscall define 3. And that does it calls into this function called do sysopen. We have several different open syscalls, right? There's openat, there's openat2, and we do, but basically, the kernel needs to handle legacy syscalls as well. So in this case, we're going to call the legacy open syscall, and it's going to call this do sysopen function. If you notice, this is a compat syscall actually. So this is actually a little different about the actual one. May still be there. Anyway, but in any case, we're gonna if you can look at all the if you look at all these syscall define macros, and you'll notice this one says syscall define 4, this one says syscall define 3. They're different definitions depending on the number of arguments. So we have to, the syscall structure will, this will set up all the goop to handle all the calling into syscall. And notice the two, they're a little different, right? There's a little bit of stuff we have to do for this one, for openat2 versus just plain open. But in any case, we're going to end up in this function called do sysopen, which calls do sysopenat2. And here we go. So now we've got for openat2, we've got a directory file descriptor, file name, and the openHow struct, which is gives it some information about what it's supposed to do when it opens. Not just the open mode, but also some things too, like whether it needs to follow symlinks, that kind of stuff. So first thing we do is we call this get name. So you'll notice here, up here, this const char user file name, and this __ user annotation lets us know that this is not a kernel pointer. This is a userland pointer, right? The address space inside your process is different than the one inside the kernel. And so when we get a pointer from userland, we have to interpret it as if it, in the context of the address space inside the process of that process. And so what we do is we call this get name file name here. And so what that does is it goes and grabs allocates a big chunk of what calls this get name flags function. And the get name function will then go and copy that value, copy the name in that string in there carefully, very carefully, into it's going to do this string copy from user and basically copy this into a buffer that the kernel can work. when we are grabbing stuff, we can't use the name directly that was, the memory directly that we pointed in, because it could change, right? If we call, if you pass in a path name, and then it starts processing, and then some other thread comes in and overwrites that path name with some garbage, or something that will cause it to buffer overrun, that could be real problematic later. So we make a copy first, and then we vet that copy very carefully. From there, use this. So in any case, we've got, so from there, we look at the file descriptor flags, or the FD flags that get passed in. And then we call this function called doFilpOpen. Sometimes you'll see a file in the kernel, is sometimes called filp, F-I-L-P, which is like in file format. It's just a naming convention. Sometimes it's used. But in any case, we call this doFilpOpen. Where is it? doFilpOpen. Maybe in a different file. So we have this doFilpOpen, and you'll see it sets, and this is essentially where the path walk happens. So what happened? So again, we have to walk a path name, which is just a string, and so this is a hugely complicated process. But basically, we call into set name data here, which basically creates this structure called the name data. Yeah. So this thing here, and this is sort of a state tracking structure for a path walk. So the name data is basically the thing that keeps track of where we are in the path walking process, and how that path walking needs to be done. Again, I'm not going to go into this in great detail because it's just way too complicated, and there's better articles for it. But in any case, we do all this. We go down into doFilpOpen, and then we do a path open at. And you'll see here first it does this thing with lookup RCU. So the kernel will, one of the really advanced things, really cool things about the kernel's path walking is that it can do it under RCU. It can do it locklessly. And this is a huge performance win. I remember when they added the lockless path walking, it was like you could see in some benchmarks we would get 20% performance increase because we weren't contending for locks all the time. So in any case, it will do this. It will attempt to do the RCU lookup first, but that doesn't always work. If you have to go do things that sleep, it will end up having to come out of path walking. And what happens is we have this. It sends back this. If the RCU if we can't do an RCU path walk, we will go back into, it will return eChild, which is sort of like a nonsensical error code in this sort of code, right? But we use that to sort of show that, to say that, the RCU lookup can't be done. You got to do what's called a ref walk, where we take references and locks and things like that and walk back. It's a lot less efficient, but it's really not that bad. From there, if we get an e-stale, so like if you're working with NFS in particular, right, you might get a stale file handle. Sometimes we see this in Ceph too. But if we get that, then we have to do something called a revalidation lookup, where we go not only path walk through, but if we have any cached entries, we go and have to go and validate that they're actually correct. So if that happens, so basically at the end of that though, we will end up calling into, so here's path open at, right? If you look here, it's got a special path for handling temp file. Here's another one for doing path open, which is sort of like a open that's opening the path name. It's useful for certain things. But then we end up down here for most files, we'll end up in this link path walk. That's where really the magic of the path walk happens. And most of the time we are not interested in most of the components. We're not terribly interested, right? They're just directories, and we get to the next one, right? But the last little bit has to be opened. And so if we go look at, I have to look here for where that happens. We do two different types of opens. And so most of the time, for most file systems, what we'll do is we'll do a lookup first. And then once we get the inode that is associated with the last path component of the Denture, or that last path component, we will then open that file, right? Turns out that is a hugely wasteful process on a network file system, right? If you have to do a lookup and then an open, then that is 2 round trips to the server instead of just 1, right? And so what we do for network file systems in a lot of cases, or some others too, is we do what's called an atomic open. An atomic open just basically says, instead of doing a lookup, we're going to issue the open directly. And then if it turns out that we get back int, and it wasn't a create, right, then we can just assume that it's a negative lookup, right? And so that saves us some round trips to the server. This was, hugely helpful once we moved to in NFS, because originally NFS v4 had to do 2 round trips to the server to do this. In any case, eventually we're going to end up down in this lookup open function, which is, again, hugely complicated. You can see here it does a delookup first, right? It tries to look up, and then it's going to come down here. But eventually, if we have a way to do an atomic open, we'll do that. And so if we look here, so that's our first stop inside the actual Ceph code. We go down into Ceph atomic open. Now, if it turns out we have, if we already know what the lookup is, right? If we already have the inode for this thing, we won't do this. Only when you have a negative denture, or you don't have a denture at all, or it's a negative denture, then we'll go try to do an atomic open. So in any case, it will go. So for Ceph, what we do is first thing we'll do is we have to take different steps depending on whether it's ocreate. We'll try to do an async open in some cases, if that's enabled. But basically, we prepare an open request here. Basically, this will build inside the kernel client. We have this thing called a CephMDS request. So whenever we need to call out the MDS, we'll allocate one of these guys, and then send, fill it out, and then send it off to the server or to the MDS to do its thing. So in any case, this prepare open request is what does that. In this case, we're doing a read-only open, so we don't care about creates or atomic open or atomic creates or sorry, not atomic creates, but an async create or anything like that, right? We're not doing. So in any case, we're going to build this request structure. I'll actually pull that up. Yes, request. Yeah, and here's what it looks like, right? You've got a bunch of fields here that get filled out. When you have the denture or an old, in some cases, like if we're doing a rename, we have an old denture. We have path names that get stuck in here, along with parent inodes. There's also things like this R parent here and our target inode, where we keep pointers to inodes that we'll need when we go to handle the reply. And then there's a bunch of other, more specialized fields and stuff in here too. So we're going to do that. We build an open request first, and then we eventually call CephMDS the do request. So this is the part, and like where we, this is the part where we call him to do the actual, to fire the thing off and send it to. And CephMDS do request just calls submit request, and then it waits on the reply. So this is a synchronous call. In some cases, we do some asynchronous calls, but in this case, it's a synchronous call. The CephMDS wait request just goes through and, or sorry, that's the wait. I don't want to look at that yet. So in any case, we have a submit request. And so what it does here is it will get cap refs if it's got certain, this our inode pointer is set. If we have a parent pointer, We are going to take cap refs for that, pin them, basically pin them. If we're doing some async creates, which we're not worried about here, and then eventually we come down here and we'll call register request. A register request will then stick it basically onto a list. See here, it just adds this thing to a list. It adds the thing to a list, and then it calls do request. Do request then actually calls down into the messenger layer. Yeah, it'll first choose an MDS, right? And because we may have multiple MDSs, we have to decide which one to send it to. Again, a pretty complex process, but we're going to skim over that bit. But basically, it's going to call into there and then check to make sure the session's okay, blah, blah, blah. Then eventually, we come down here to send request. So that will go and stick the thing onto the hand the thing off to the messenger to be sent off onto the wire. Once we're done there, we put references or whatever, and then in this case we're going to wait for the reply to come in. Yeah. So anyway, down here we've submitted the thing. We call down in here to wait for the reply, and when the reply comes in, we'll process it. So if you see here, here's wait request. And so we have some handling for stuff if if it got aborted in the meantime, depending on what how it's handled. And then we'll if it got an error, we'll return an error in this case. But in any case, what we'll do here is open. Right. So we're down here. Yeah, down here. So we will return here, and so we've got the result now at this point. Right. In this case, we're not going to get ENOINT because we're going to pretend the file's already there. And then you have to some special handling here because it has to be we are sort of doing a combined open and lookup at the same time. So in some cases we have to actually handle the result of the lookup in addition to the open. But down here, eventually, we're going to finish open. So this will end up essentially fully instantiate the struct file and give us a file description that we can then use to do other things. All right, and then we go back. All that will unwind and go back to userland once we've got a file description, that goes back to the back into the VFS layer. The VFS will then attach a file descriptor to it, and then we hand that file descriptor back to userland. So now userland is going to say, let's go and read this file. Right, we're going to read both we've got a file descriptor. We're going to pretend that it's stuck a buffer on the stack or whatever, and then we're going to read the first 4K of the file. Right. So now what we do, we have this call find 3, 3 argument struct. Going to find the one for read. It's a read write C. Yeah, here we go. All right, and here's a read. So we have this. We're going to do it. It calls into this function called casesRead. Which goes and figures out where the position of the file is and whatnot, and then calls to this function called VFSRead. A lot of the generic VFS layer, handling is prefixed to this VFS underscore. When you see those, usually that's a pretty good indicator that it's a generic structure or generic function that is used across different file systems. In any case, VFSRead calls in and let's see if we can find VFSRead. Yeah, here it is. So VFSRead does some, it does some checks. Is this? Can we actually read from this file descriptor? Is it? Is the buffer we're dealing with in our address space, yada yada, right? But eventually we come down here. It's going to call this other read RW verify area as well, which does some of it does some things like make sure we're not trying to read beyond the the head of or we're not trying to read the a negative offset into the file or something. All sorts of there's lots of ways that you can try to trick the kernel, and so it has to check all this stuff. But in any case, we've got here we are, RW verify area. And then we come down here, and if we've got this file fop read, we'll call that. We don't have that for Ceph, so we have a read iter function. So if that is there, if that is set, we will call new sync read, and that. And I hate this part. Sometimes in the kernel, they'll just have this sort of call read iter. Right? So where we have this sort of useless wrapper function instead of just calling the thing directly. Call read iter. So look at that real quick. Yeah, and all it does is just call this read iter function. The reason we have this is that the original kernel, we would pass down a buffer and stuff, but about 7-8 years ago, we went pretty big into using this struct IOD iter inside the kernel, all over the place. And what this is it's sort of like when you need to iterate over a user, a buffer of some sort, then we can pass this in, and we can have these iterators of different types. So there's some that are referred to userland buffers, there's some that refer to kernel buffers, some that may refer to a pipe, that sort, all sorts of stuff, right? And so this allows us to use a lot of the same code without having to worry so much about what the destination or the source buffers look like. So we use these things all over the kernel. All right, in any case, we're going to call read iter, and then for us, this becomes Ceph read iter. Let me take a pause here for a second. Anybody have any questions? Everybody asleep? Oh, okay. In any case. All right, so anyway, here we are as Ceph read iter. And so what, so basically we call this anytime we get like a read syscall from userland. We also will call this for things like if you've got an mmapped area in a Ceph file and you fault in that page, right? You try to read from the mmap or try to read off of the mmap. It will turn that into a read, to a read that will to populate the page. So in any case, we have this read, or sorry, actually that will call read page. That doesn't call into this part. But in any case, the read iter is where we call in to do handle a read for Ceph. Right? So we do all sorts of stuff. First, we see if the inode's shut down. If you forcibly unmount the thing, or if it's we've been blocklisted, we consider that to be we shut down the access to the inode, and then we'll return it. We have some special handling depending on whether it is IO direct or it's an O direct open or not. If you're not familiar, then O direct is a way for to tell the kernel that you want to bypass the page cache and either read into or write to some buffers directly. And this will almost always cause an on the wire read or write. We come down here. So here we have some flags. We have to start deciding like how we're going to do, right? So Ceph is a bit special. Most file systems use the page cache unconditionally. So the kernel tries really hard to cache file data so that it doesn't have to go and reread it or whenever it needs to be accessed again. So the sort of one of the operating principles of Linux from very way back is that any RAM you have that's not used is wasted, and so we try to use most of our RAM in the kernel for page cache for buffering disk reads or buffering reads from file systems in general. In this case, we have some, so we have to decide whether we can use that or not. And so in this case, we have some cases like if we're not doing a direct I/O, we don't have this fsync, CephFS flag, which is a I/O cuddle that can set, you can force a file to be synchronously accessed. Then we will try to get the cache cap, the FC cap. There's also this lazy I/O stuff here, which is somewhat poorly defined, really. So we won't go over that in detail, but it's there. So the first thing we'll do here is we'll call into ceph get caps, and this will issue a, if we've got caps already for this inode, we'll take references to them to ensure that they don't get released while we're trying to use them. But if not, then we have to call out to the MDS and request them. So ceph get caps does that. I'll just take a quick look real quick. Yeah, and so we've got a bunch of stuff here. Again, a hugely complicated process. Go and try to get request caps from the, basically this thing just calls, if we don't have them, we'll just call try get cap refs here. And that will call out to the MDS to say, try to give me these caps if you can. Okay, in this case, let's just pretend we got the caps, because in most cases we do. So depending on whether we got caps or not, if we didn't get caps, then we're going to try to access this thing synchronously. And so we have this direct read-write code here that handles doing DIO reads and writes if it's a direct IO read-write. If it's not direct IO, we do it. We can call it synchronous read here. And that will just go and actually issue a read on the wire for the particular range that we're trying to read, or a number of reads if it's a very large read, for instance. But most of the time we end up calling, we get cache caps, and we call down here into generic file read editor. This calls back out into the VFS, and what it does is this is basically the so if we're not doing direct I/O or synchronous I/O, then we are doing page cache I/O, and so all the reads and writes in this case will be page aligned. And so we can look at generic file read editor. And this is just a generic helper function for most processes. Do if we're doing I/O direct, whatever. Then we will call it, but eventually it's going to call down here and do this file map read. Yeah. File map read calls down here. It will grab page cache pages, kind of get them prepped and ready to go. Check the size. It does a bunch of other checking too. Then. Oh, where's the actual thing? Sorry, I gotta find where it actually does the read. That's the copy. It must be. File map get pages, I guess is where that happens. Yeah, down here. And so basically we go down here, and you'll notice here too, most of the time, so historically the kernel has always operated on most computers that we work with have what's called an MMU, and the MMU operates in a memory management unit, and the MMU operates in units of pages. Typically those pages are 4K. We are in the middle of a huge churn in the kernel right now, where it will, where we are converting from a, so the problem is that memory has gotten, memory sizes have gotten really huge, right? And so tracking 4K pages in this day and age is pretty wasteful. You can imagine we have to have a structure for every page in the files in the kernel, and that we have millions of these things because because they're all tracked at 4K granularity. That turns out that most MMUs can work with larger pages without too much, without any problems. But the kernel is not equipped for that currently. So we're moving to a new structure that's called a folio. The idea, you have a page, right? A folio is sort of a gathering of pages. We've had ways of ganging together pages before in the kernel, but it was always really poorly defined. Sometimes you would get something that was called a compound page, and it was really not everything in the kernel was really equipped to deal with those. The page cache in particular never did that. So we're trying to move the kernel's page cache eventually to work with larger pages. And as part of that, we're converting a lot of where we have traditionally operated with page pointers to something called a folio. And so that's what this is all about. In any case, we've got here's some batch handling. If you've got a bunch of big folio, but in any case, we have this folio test read ahead. If we're able to do a read ahead, the kernel will we can try to expand that read to something larger. So let's pretend that we're going to be allowed to do a read ahead here. And so we look here, call this page cache async RA. May not be in here. Yeah. And so in any case, we call this, and then it calls down to this on-demand read-ahead function. And then eventually we're going to get into calling the read-ahead function for Ceph. Okay. Yeah, Ceph has, and so Ceph, we traditionally had our own read-ahead function. And read-ahead is actually fairly new. If you look at older kernels, you'll see something called read pages, which is the old style method of doing it, which was pretty wasteful with page locking. So we've moved to a new, like I said, the internals are very fluid in Linux, and so we change stuff all the time. And so read ahead is the new way to do multi-page reads. And so we end up doing we call into this NetFS read ahead. And so the NetFS layer is a new thing too. If you look at some of these old kernels, things like that, you did stuff like read ahead, or that had the old read pages operation. You would notice that it spends a whole lot of time doing, setting up pages and handling page flags and getting references to the pages and stuff like that. A lot of that stuff is really sort of a pain in the butt for a network file system. And so we are trying to consolidate a lot of that into a new layer called the NetFS layer. So the NetFS layer has a new operation struct right here. So this is, you can see the NetFS request ops. And so basically this is a much more natural interface for dealing with network file systems. So rather than having to say, okay, giving us a pile of pages and say, okay, fill all these, set all these pages up for a read and fill them up. The NetFS layer calls it to us and says, here's a pile of pages we're already prepared. Let's go and fill them for us. And so we end up with this. We do some setup, with these things. We have this init request function that will go and sort of prep the thing and decide whether it needs to be inlined. We can begin cache operation too. And we got a number of things here that we do. The other nice thing about the NetFS layer is it encapsulates a lot of the gory details for handling FS cache. And eventually we have FS script. So in any case, but eventually we're going to end up with this Ceph NetFS issue read. And this is where the actual read happens. So it has given us this NetFS IO subrequest. So when we issue a read, that read may span for instance, multiple Ceph objects, right? And so we might have to issue 2 actual read calls onto the wire to fill it. So the first thing it does is it tries to, we call a number of functions to sort of like expand the read ahead, and then we also have to do some clamp the length, like if the thing we can't read beyond the end of the object in Ceph, right? So we have to clamp the length at where that object ends, and that's what this is all about. It looks at the object mapping and does that. But eventually, we're going to get down to doing a NetFS read, and we spin up a new OSD request. That's what this guy does. That goes down into here. We go, we get what's called an X array of pages from the IOD iter. The IOD iter is what we're copying into. We get we go and grab an X array for this thing, and then we call this IOD iter get pages alloc, which basically just allocates a bunch of pages, page cache pages for us, it grabs the page cache pages in the right locations and gets pins them basically and gives us back an array of these pages. And then we hand that down. We stuff all that into the OSD request. We set a callback for when it goes, and then we go and start that request, and then we return. So the request is allowed to, so that request will run asynchronously, right? It will. So if you've got multiple reads, we're going to go and we'll boom, 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 fire several of them off, and then and collect all the replies. So eventually, when the reply, I'm not going to dive down into the OSD code at this point, but eventually this code will come back. Then when the reply comes in, the OSD code handler will call finish NetFS read, and then we go and look at the result. Like it may be that there's no object there, right? If there's no object there, we get back an ent, and then we pretend that is a 0-length read. If we get blocklisted, then we have to deal with that. If the read was shorter than we had expected, right? Let's say we tried to read a whole 4 meg object off of the OSD, and then it turned out that it was not, that it wasn't that long. We need to tell the NetFS layer to clear the last thing. That's what this flag does. And then eventually we call this NetFS subrect terminated, which tells the NetFS layer that okay, we're done, and here is the new. It either ended with an error or with a successful read, and then we go and put the page references. We have to hold references to the pages while we're filling them, sure they don't get purged out of the cache. And then when we're done, we put those up. And then we call IPut as well to put the reference to the inode that we're holding. Every time we send off an OSD request, we take a reference to the parent inode to make sure that it doesn't go away. Right, now we have populated pages or a populated page in this case. Right? So now we've gone and go back into the iter. So we're back in here now at this point, and generic file read iter is now returned. We go and put cap refs, we put our cap references and that sort of thing. We have some blocking to ensure that we don't mix buffered and direct IO. And we have some handling too if it turns out that we had to retry because maybe we didn't have the right caps or there's some other problems. Ceph has a lot of really strange handling for things. So if we hit a file or a hole, zero out the end. So in any case, we've got all this stuff. And then eventually we bubble all that back up to userland and say, okay, we got to read, right? So let's say we read 100K or whatever. Now we're going to close the file. Let's call Let's find close right here. And here's this call define one, right? We close. So now we're going to close FD. So we tell the that will allocate the. Oops, sorry, that's the wrong one. There. It will find the file. So we've given it a file descriptor, right? It goes and looks up that file descriptor and says, all right, we're going to close this, or this file description, and it's going to close it. So it calls this filter close. Filter close. Here? No, of course not. Almost to the end of my hour. All right, and now filter close goes and if it's a writable file descriptor, we're going to flush whatever data we can generally, and remove any POSIX locks, right? And then we put the file descriptor, and so fput is a wrapper around this function, fput, around underscore fput. This does a bunch of other stuff, but basically we're going to call this. Eventually, we call down to the release for that. And then this is the Ceph release function. In this case, it's not a directory inode, so we open this guy. Yeah. And so we get rid of the FS cache cookie that we were holding for that, and then we put whatever fmode we've got for the file, so indicate that we're no longer holding this file open for read. And then we free that Ceph file info that was attached to it, attached to that struct file. And then we wake up anybody that happened to be waiting on cache for this. And at that point, that's pretty much it. We will go and the VFS will do its thing to free that file descriptor and free whatever, free the struct file as well. And then that's the end. And that's about all we're going to cover today. Any questions?
Jeff, I had a question in the function Ceph atomic open. It said in the comment, it said, if the file of symlink is non-existent, the VFS retries. So does VFS keep retrying, or what's the idea behind that?
Okay, sorry. Let's see. Which part were you talking about?
Like if you go to the comment on top, it says if the file is non-existent, or
oh, that looks like that comment's just bogus.
So the VFS keeps retrying. I mean, when does it?
If we get a if we get a non-existent file or something, return once. Yes. The calling convention for atomic open has changed. I don't think this comment is actually correct. But basically, yeah. I mean, when you if it turns out that the file is non-existent, basically we don't retry really. It just returns int at that point. We're doing a read. Essentially, instead of doing a separate lookup, we just do a read or do an open and try to get that. Yeah, this comment is bogus. I probably should spin up a patch to get rid of it. At one point, we would return 1, and we may still do that internally, but a lot of that has been changed to use this finish open structure. And so if we've got if finish open is what actually handles most of this. So in fact, we can take a quick look at it if you want. We'll just call it do Denture open. To finish the open. Yeah, so that comment is bogus, I think. Sorry. Unfortunately, we have a lot of those in the kernel. Places where things have changed and people didn't update the comments.
Yeah, and in atomic open, you said one of the calls is synchronous. I didn't get that. Was it submit or wait entry? You said the call is synchronous?
I'm sorry, can you repeat that?
You said one of the calls is network calls is synchronous in Atomic Open. Is it submit a wait entry or is it?
Yeah, it is synchronous. Because I mean we can't return. Well, you know, we can we do allow async opens sometimes, right? For instance, if the kernel, if we have, so if atomic open, is called in a very special circumstance, right? We either don't have a cached entry for this thing, or we have a negative entry. Okay, so if so, we either don't know what the provenance of this entry is, or we know that it doesn't exist, right? And then it will call atomic open to do the open and lookup at the same time. That will allow it to instantiate a entry if it needs to. And also, if it turns out that we're wrong, right? Because sometimes sometimes like if, when we have negative entries, sometimes they could change on the MDS and and the client doesn't know, right? And so if that happens, so atomic open allows us to, if it turns out that we thought this file didn't exist, but now it turns out that it does, and we didn't do a create, and we're not doing a create, right? So it turns out that it does exist. We will issue the open call to the MDS, and if that comes back, then we can go and instantiate the entry. Say, this entry does exist. We can attach an inode to it now and turn it into a positive entry. So this is a pretty complex situation, and quite frankly, Alviro hates this, right? We've been trying to find for about a decade now, figure out a cleaner way to do this, but it's fortunately not trivial. Atomic open is like kind of one of those kludgy things that we added to work around a problem, and it was never very elegant to begin with, and it still isn't. So, but yeah, in this case, we will always do a synchronous RPC to the MDS. So we are always going to call the MDS on there because we have to, because we don't know. We either think the thing doesn't exist or we don't know. So we have to call the MDS either way, and we have to wait for the response to come in.
Okay, got it. Yeah, and the final question I had is, there was one of these PRs, of introducing async IO and libCephFS, and one of the questions asked was, how do we detect end of file when reading? And so you said you need to, because we read from a bunch of objects, and you always keep track of the inode size, and then you read from those. That's pretty unique to our file system, right? Where to detect end of file, we need to do that.
Yeah, to some degree, yeah. I mean, it's not. I mean, we have some of those similar situations with NFS as well. We're doing PNFS in particular. Sometimes we may come back. It may have a very similar kind of thing where it is reading from some sort of aggregate of multiple server, multiple backends or whatever, multiple objects. But yeah, for Ceph, it's we have to basically query the MDS and say what is how long is this file, because the files can we can't trust that just because we got a short read that's where the file actually ends, right? If we got a short read, it may just mean that the end of it is sparse, and so it just didn't, that part was never written, but it was maybe truncated out to a larger size. In that case, we have to go and fill in that part that doesn't exist with zeros for the response. Does that answer your question?
Yeah. So so we need to keep track of the inode size very carefully to make reads. Okay.
Yes, definitely. Yeah, it's pretty tricky to get it right, actually.
Yeah.
There's a lot of handling for the inode size, and I'm not even 100% convinced that it is all race free. My guess is that there are probably some cases where we could race and get the size wrong.
Okay. Thanks, Jeff.
Yeah, this is an area that probably could use some improvement if you want to try to understand it and figure out how it works.
Okay.
Yeah. Any other questions? All right, if not, thanks for coming. It was a pleasure to talk to you all. So let me know. I'm going to plan to do at least probably one more walkthrough covering some other areas as well. But that'll probably be in another week or two. So thanks for coming. See you later.